Hi, thanks for joining me. Today I'm going to be showing you a fun non-standard proof. I want to prove that there are infinitely many prime numbers. Now this is a result that has been around for quite a while, over 2,000 years in fact. The earliest proof dates back to Euclid, and that was a proof by contradiction. So whenever you're introduced to proof by contradiction, this is generally the standard example they give. So I'm not going to be doing that proof today. There are probably hundreds, if not thousands of videos on YouTube proving that. I am going to be doing a different one, and the only assumption I'm going to make is that pi is irrational. Now this is certainly true, pi is indeed irrational, but most of the proofs for that are kind of either complex or they're not particularly intuitive. I don't yet have a video in which I prove that pi is irrational, but if you want one, let me know in the comments down below, and I'll make a video in which I prove that pi is irrational. But that's the only thing I'm going to be assuming today. If you haven't seen any proofs that pi is irrational, just Google it, you'll find some. But yeah, I'm going to be assuming that, starting from pi is irrational to prove that there are infinitely many primes. So there's quite a nice connection between pi and the primes. Anyway, let's get stuck in. Okay, so the first thing we want to do is quickly state a lemma. Okay, so we have this function f from the natural numbers to the reals, so the positive integers to the reals, and it satisfies this thing here, that f of ab is equal to f of a times f of b for all positive integers a and b, and we also have that f of 1 equals 1. So this is sometimes known as a completely multiplicative function. Okay, and suppose we also have this thing here, that the infinite sum, so the sum from n equals 1 to infinity of f of n is less than infinity, so this series here converges, and we also have that for any prime number p, the magnitude of f of p is less than 1. Then we have this conclusion here, the sum from n equals 1 to infinity of f of n is equal to this product here, so the product over all the primes of 1 minus f of p inverse. Okay, so I'm not going to prove this in this video today. It's not too difficult. You start from the right hand side here, and you look at this guy here, so 1 minus f of p inverse. Well, that's just 1 over 1 minus f of p, but because this thing here is less than 1, we can write this as an infinite series. It's just 1 plus f of p plus f of p squared, plus f of p all squared, plus f of p all cubed, and so on. And then we're taking the product of those, and then if you sort of expand that out, you're going to see that you can get f of any natural number, and just using this property here and combining it. So I'll leave that sort of as a little exercise for you, but we're just going to use this in this video here, and that's just kind of to keep this video short. Okay, so we're going to use this lemma in just a second. Let me clean the whiteboard and we'll continue. Okay, so I've written up an infinite sum identity on the whiteboard. Pi over 4 equals this guy here, the sum from n equals 1 to infinity of minus 1 to the n plus 1, all divided by 2n minus 1. This is certainly true, and I've made a video in which I prove it, so I'll leave a link for that in the description below. So if you haven't seen this result before, go and check that video out once this one's finished. Okay, but yeah, so we're just going to use this. I'm not going to bother proving it again because, again, I've already made a video in which I prove it. Now what we want to do is use the lemma. So we kind of want to use this right hand side and mold it into the sum from n equals 1 to infinity of some function f of n, then just check that f has the properties that we required it to have in the lemma, and then we can go ahead and use the result of the lemma. Okay, so firstly let's have a look at this and perhaps just write out the first few terms. So this is just, well, 1 minus a third plus a fifth minus a seventh plus a ninth, and so on. So it's just the reciprocals of the odd integers, and then we've got alternating 1 minus 1, 1 minus 1, and so on. Okay, and now what I'm going to do is just include the even terms. And oopsie daisy. So the reasoning for that is because, remember, we want to write this in the form sum from n equals 1 to infinity of f of n. But of course that includes all the even n's as well. So I want to just add on the even terms, but make sure I'm multiplying them by 0. So let's just write this as 1 plus 0 over 2 minus a third plus 0 over 4 plus a fifth plus 0 over 6 minus a seventh plus 0 over 8, and so on, plus 1 over 9, and so on. Okay, this might seem like a bit of a weird thing to do, but again, it's because we want to use the lemma that we just proved. So we want to write this in the form, the sum from n equals 1 to infinity of some function f of n. Okay, well, if we look at this function here, f of n, and I'm going to define it to be this thing here, 1 over n times 0 if n is even, 1 if n is congruent to 1 mod 4, squeeze that in there, or minus 1 if n is congruent to minus 1 mod 4. Oopsie daisy, that says mod 4 there. Okay, so f of n is this function here which I'm defining, and now I claim that this guy here, so the sum from n equals 1 to infinity of this f of n is equal to this thing here. So let's just have a look at why that's the case. Firstly, we need that all the even terms are 0, and that's quite clear because we get 0 times some constant, so these even terms are all 0. Then we've got to check that the odd terms are certainly 1 over the odd number, then times by either 1 or minus 1. So it's all the odd terms. For f of n, we get this 1 over n, and then it's times by either 1 or minus 1. And that's because if we look at any natural number n, which isn't even, then certainly it's odd, then it's either 1 mod 4 or it's minus 1. It's one of the two. Okay, and then we've just got to check that the signs match up. So if you look at, say, the first term, so when n equals 1, that n equals 1 is congruent to 1 mod 4. So that means that f of n would be 1 over n times 1, so 1 over 1. So that checks out. Let's check the next one, 1 over 3. So we should hopefully get minus 1 over 3 when we plug in f of 3, sorry. So f of 3 is equal to 1 over 3, but then 3 is congruent to minus 1 mod 4, so we have to look at this thing here. So we get minus 1 over 3. So that works perfectly, and then the same holds for all the other ones as well. So this function in fact works. So sum from n equals 1 to infinity of f of n equals this guy here. So now what we want to do is just check that f, this guy here, has the properties that we want. So f of ab equals f of a times f of b for any ab, f of 1 equals 1, and that the magnitude of f of p for any prime number is strictly less than 1, and hopefully then we'll be good to go and we can apply the lemma. Okay, let me clean up the whiteboard, bring it to the top, and we'll continue. Okay, so we showed that pi over 4 equals the sum from n equals 1 to infinity of f of n, where f of n is this function here, and now we just have to check that f satisfies the properties of the lemma. So first let's check the easy one, that f of 1 equals 1, and that kind of, I'm not even going to bother writing that down, it's just straight from here. When we plug in n equals 1, we get a 1 over 1 here, so that's just 1, multiplied by this guy here, and because n equals 1, well that's 1, that's congruent to 1 mod 4, it's just 1 times 1, which of course is 1. Okay, so f of 1 equals 1, great. Now we've got to check that f of ab equals f of a times f of b for any ab. So we want to prove this thing here. Firstly, if either a or b are even, then certainly ab is going to be even. So on the left hand side we've got f of an even number, which is clearly 0. So on the left hand side we've got 0. But because either one of a or b is even, let's say a is even, then on the right hand side we've got f of a, which of course is 0. So we've got 0 times something, so that of course is going to be 0 as well. So we've got 0 equals 0, so that's great. So we know that this thing holds if either a or b are even. So now let's assume that a and b are both odd, and we just sort of got to go case by case of the congruencies mod 4. So if a and b are congruent to 1 mod 4, well, what do we get on the left hand side? Well, this implies that AB is congruent to 1 mod 4. Okay, so f of AB, oopsie daisy, is equal to 1 over AB times 1, because AB is congruent to 1 mod 4. So this thing here is just 1 over AB. Okay, and f of A times f of B. Well, A and B are both congruent to 1 mod 4. So this thing here is just 1 over A times 1, because f of A is just 1 over A times 1, because A is congruent to 1 mod 4, times 1 over B times 1. Okay, for the same reason, and this of course is just 1 over AB. So we get that this guy equals this guy, and we've shown that it holds in the case that A and B are both congruent to 1 mod 4. And I'll sort of leave it as an exercise. It's kind of trivial, kind of just laborious and kind of straightforward, just to prove that this also holds if one of AB is congruent to minus 1 mod 4 and the other one is congruent to 1 mod 4, and in the last case when both of them are congruent to minus 1 mod 4. But it essentially boils down to the fact that minus 1 times minus 1 is 1. Okay, but yeah, so we've sort of shown the second property, that f of AB equals f of A times f of B for all AB, and the last thing we've got to do is just prove that the magnitude of f of P is less than 1 for all P, where P is prime. Well, the magnitude of f of P is just simply 1 over P if P is odd. Now obviously if P is even, in the special case when P is 2, then f of P is 0, so of course that's got magnitude less than 1. So we may assume that P is odd, so the magnitude of f of P is just 1 over P, but obviously then P is at least 3, and this thing here is clearly going to be less than 1. Okay, so we've checked the property, so f satisfies the lemma, so we can apply the results of the lemma. So let me just clean up the whiteboard and we'll continue, and we're almost done. We're almost done. Okay, so now I've just written down the result of the lemma because we've just checked that f satisfies the properties that we need. So the sum from n equals 1 to infinity of f of n is equal to this guy here, the product over all the primes of 1 minus f of p inverse. Okay, so let's just have a look at this thing here. Now we're going to assume for contradiction, or suppose for contradiction, that there are finitely many primes p, in which case if we just look at this thing here, f of p, well, notice that f of p is always going to be some rational number. It could be negative, it could be positive, but it's clearly 1 over n, or 1 over p, which is rational multiplied by 0, 1, or minus 1. So it's either going to be 0, 1 over p, or minus 1 over p. Either way, it's going to be some rational number. So 1 minus f of p is rational. So if you take its reciprocal, that's also rational. And now because we're assuming that there are finitely many primes, we're just multiplying finitely many rational numbers together. But when we do that, and you can prove this by induction, the product of finitely many rational numbers is going to be rational. So we have that this thing here is rational. Okay, but if we just work back, we have then that pi over 4 is rational. But then just sort of multiplying both sides by 4, that tells us that pi is rational. And we arrive at a contradiction, because this, of course, then implies pi is rational. But remember, we're assuming, and it's also true, that pi is irrational. Okay, so we arrive at our contradiction, and that ends the proof. Okay, one thing I guess I should have mentioned, sort of an assumption we also kind of made, but I guess it's one of those things, it's a fundamental theorem of arithmetic, that every single natural number, every single positive integer, has a unique decomposition into primes. Okay, and we use that in the to prove the lemma. But yeah, that's kind of just a small subtlety. But this is a really neat proof, certainly not your standard proof that there are infinitely many primes. I hope you have enjoyed this proof. Yeah, I'll catch you in the next one. Have a great day.